solid-state batteries are being sold as the answer to everything. Faster charging, longer life, higher safety, fewer compromises, a future where waiting disappears and limitations quietly fade away. That's the promise. And if you've been watching headlines long enough, it starts to sound familiar. Every few years, a new battery technology arrives with numbers that feel almost unreal. Numbers that don't just improve what we have, but seem to replace it entirely. 5-minute charging, hundreds of watt-hours per kilogram, cycle life so long it outlives the machine it's installed in. It sounds like the end of the story. But it is. Because here's the part most coverage skips, the part that matters more than any spec sheet, the part that determines whether a battery changes the world or quietly disappears into a niche you never hear about again. What kind of work is this battery actually built to do? Not what it can do in a lab, not what it can survive in a controlled demo, but what role it's meant to play when it's bolted into a real machine, working day after day, under heat, vibration, load, and human expectations. In the real world, EV batteries don't all serve the same purpose. Some are designed to store energy efficiently and deliver it gently over long periods. Others are designed to dump power instantly, absorb punishment, and keep working even when conditions are far from ideal. And when those roles get confused, that's when disappointment starts. That's why in this video, we're not ranking batteries. We're not declaring winners. We're separating energy batteries from power batteries, using Donut Labs' solid-state claims and aluminum-ion batteries as a contrast. Before we go any further, pause for a moment and ask yourself something honestly. Would you rather have a battery that charges in 5 minutes? Or one that can deliver full power, again and again in extreme heat without hesitation? And when a battery sounds like it can do everything, what is it quietly not optimized for? That's what we're breaking down today on Teslaris. And if this kind of analysis matters to you, if you care less about hype and more about where technology actually fits in the real world, make sure you stay with the channel. Teslaris exists for one reason: to slow the story down, question big claims, and focus on the limits no one likes to talk about. Now let's get into it. When people hear 5-minute charging, they instinctively picture power. They imagine a battery that can swallow electricity instantly and then unleash it just as aggressively. Something almost violent in its capability. Something that bends physics out of the way. But in battery engineering, fast charging and sustained power delivery are not the same thing. They are different stresses, different priorities, different internal battles happening inside the cell. Donut Labs' solid-state battery numbers point very clearly in one direction, even if the marketing doesn't say it out loud. Energy retention and longevity. A claimed 400 watt-hours per kilogram is not about pushing current. It's about packing as much energy as possible into a given mass. That kind of design demands dense electrode structures, extremely stable interfaces, and tightly controlled internal environments. Those are the choices you make when your goal is range, safety, and long service life. They are not the choices you make when your goal is sustained high power output under constant load. The same pattern shows up in the cycle life claim. Numbers like 100,000 cycles don't come from brute force. They come from restraint, from minimizing mechanical stress, limiting temperature spikes, and avoiding violent swings in current. In other words, the battery survives by refusing to live at the extremes. And that is exactly what you want in vehicles that charge often, discharge moderately, and repeat that process for years without drama. Even the 5-minute charging claim fits this pattern more than most people realize. Fast charging does not automatically mean high continuous power output. Many batteries are engineered to accept short, intense energy bursts during charging while remaining conservative during discharge, precisely to protect their internal structures over time. So when Donut Lab positions its solid-state battery as fast-charging and ultra-long-lasting, the message is that this battery does everything. The message is quieter than that. This battery is extremely good at holding energy, at surviving repetition, at staying stable, not at acting like a constant power pump under heavy industrial stress. And that distinction matters, because the moment you ask a battery to deliver sustained high power in heat, under load without rest, you are no longer testing energy density. You are testing whether it is a power battery at all. That's where the comparison starts to shift. If Donut Lab's solid-state battery is obsessed with how much energy you can store safely, and for how long, aluminum-ion batteries are built around a completely different obsession. How fast energy can move without breaking the system. Start with the number almost no one leads with: power density. Most aluminum-ion cells reported in peer-reviewed research operate comfortably at 10 to 20 C continuous discharge, with demonstrated pulse discharges reaching 50 C and even beyond 100 C in controlled environments. That means the battery can deliver its entire stored energy in minutes, sometimes seconds, without structural damage. Now compare that to automotive lithium-ion cells. Even high-performance EV cells are typically designed for 2 to 3 C continuous discharge, with higher bursts allowed only briefly before thermal throttling begins. That limit isn't software, it's chemistry, it's heat generation, it's electrode stress. This is why aluminum-ion batteries look underwhelming on a range chart, yet suddenly become unbeatable in machines that never stop working. Energy density tells the opposite story, and deliberately so. Aluminum-ion cells usually land between 40 and 70 watt-hours per kilogram, with optimistic lab demonstrations pushing toward 90 or even 100. That's a fraction of lithium-ion, and nowhere near Donut Lab, claimed 400. But lower energy density comes with a hidden advantage. Less internal heat per unit of power delivered. You're not cramming massive energy into a tight structure. You're spreading it out, and that dramatically reduces thermal stress during rapid charge and discharge. That's why aluminum-ion systems can operate in environments where cooling is minimal, passive, or sometimes non-existent. Cycle life numbers can be confusing until you understand what kind of cycle is being measured. Aluminum-ion batteries are not optimized for slow, deep 0 to 100% energy cycles. They excel at something else entirely. High-frequency microcycles. Charge, dump, recover, repeat. Many studies show 20,000 to 50,000 cycles with minimal degradation under high-rate conditions. Exactly the pattern seen in industrial systems, grid-adjacent storage, and heavy machinery. And this matters because real machines don't behave like personal cars. A port crane, a mining vehicle, or a grid stabilizer may cycle its battery hundreds of times per day, but only across a small state of charge window. Lithium-based energy batteries hate that. Aluminum-ion doesn't. Thermal tolerance pushes the divide even further. Aluminum-ion chemistry remains stable well above 60 to 80 degrees Celsius, temperatures where most EV battery packs are already deep into derating, active cooling dependency, or outright shutdown. In hot climates or sealed industrial environments, this difference alone can determine whether a battery is usable at all. And once you see that, a pattern starts to emerge. Aluminum-ion batteries show up in heavy industrial equipment, in grid buffering and frequency regulation, in rail systems, port operations, and regenerative braking capture. Not because they're cheaper, not because they're more advanced, but because they can absorb abuse without changing their behavior. So when you place aluminum-ion next to Donut Lab's solid-state battery, The conclusion isn't that one is ahead of the other. It's that they answer completely different questions. For Donut Lab, the question is how much energy can we store, how safely, and for how long. For aluminum ion, the question is how fast can energy move, how often, and under how much stress. And once you see that, the real issue becomes obvious. Comparing these batteries directly is like comparing a fuel tank to a hydraulic pump. They don't compete. They coexist as long as you put them in the right job. This is where the real risk shows up, not in the chemistry but in the assumptions people make. When someone hears 5-minute charging and 100,000 cycles, it's easy to assume a battery like Donut Lab's solid state should work everywhere. Passenger cars, heavy trucks, industrial machines. Why not just use the best battery for everything? Because batteries don't fail when they're bad. They fail when they're misused. High-energy batteries prioritize energy retention over power delivery. Packing 400 watt-hours per kilogram into a compact structure means tighter electrodes, higher internal energy concentration, and stricter thermal boundaries. Even if a solid-state electrolyte reduces fire risk, it does not eliminate mechanical stress or heat accumulation under sustained load. This is why fast charging does not automatically translate to high continuous discharge. A battery that can absorb energy extremely quickly is not necessarily optimized to dump energy continuously at high power. Those are two different stress profiles. One stresses ion transport during charging. The other stresses heat dissipation, electrode stability, and structural fatigue during discharge. That distinction becomes painfully clear in industrial duty cycles. Think about machines that operate at near constant load, construction equipment, port vehicles, mining systems, grid-connected assets. These machines draw high power for hours, not seconds. In those environments, even brief thermal throttling isn't an inconvenience. It's a failure. And this is where aluminum-ion batteries quietly outperform energy-dense alternatives. Because they are designed around power throughput, not energy packing, they tolerate sustained high currents with far less derating. Lower energy density means lower heat accumulation per unit of power delivered, which allows the system to behave predictably even when abused. The risk is that Donut Lab's battery can't handle power. The risk is assuming it should. And this matters for manufacturers far more than consumers realize. Designing a machine around the wrong battery forces compromises everywhere else. Larger cooling systems, conservative power limits, aggressive software throttles, shortened service intervals. On paper, the battery still looks revolutionary. In practice, the system becomes fragile. This is why we don't see Donut Lab's solid-state battery debuting in heavy industrial platforms. Not because it isn't impressive, but because its strengths don't align with those workloads. So the real takeaway isn't that aluminum ion is better, or that solid state isn't ready. It's that modern battery design has become specialized, whether marketing admits it or not. And once batteries become specialized, the question changes. It's no longer which battery is the best. It becomes which battery fails most gracefully when pushed beyond its comfort zone. And that's a question spec sheets never answer. To understand where these batteries realistically fit, we have to look at Tesla, not theory. In 2024, Tesla delivered roughly 1.8 million vehicles globally. Internal targets and analyst estimates point to roughly 2.2 to 2.5 million vehicles per year by 2027. At that scale, Tesla consumes on the order of one, including its own structural formats, until a new battery proves not that it's better, but that it can show up at massive scale without surprises. Which brings us to the real tension. If solid-state batteries aren't ready to scale for mass-market cars, and aluminum-ion isn't meant for cars at all, then what problem does Tesla still need a new battery to solve? That's the question we'll tackle next. The takeaway here is simple. Donut Labs' solid-state battery isn't too good to be true. It's just built for a different job. And aluminum-ion isn't behind. It's aimed somewhere else entirely. In the next video, we're going to zoom out and ask the uncomfortable question. What happens when battery breakthroughs don't fail, but still don't fit mass-market EVs? If you don't want to miss that logic chain, stay with Teslaris. We'll see you again in the next chapter of this battery series.